My name is Dietmar Hildenbrand. I am from the University of Technology of Darmstadt in Germany, and I am presenting the power of geometric algebra for Mathematica. Thank you very much for this, for the invitation to present my topic to you, and welcome everybody. I want to talk about the power of geometric algebra computing for Mathematica. And I think, first of all, I have to explain a bit what geometric algebra is. Does somebody knows geometric algebra? Okay, and Clifford algebra? Also, okay. So I will give you some information about geometric algebra, then present some engineering applications that we are using at our university, and then present our computing technology for geometric algebra and how it can be used also for Mathematica. Okay. So, first of all, some properties of geometric algebra. A very nice thing that is that it unifies a lot of mathematical systems that we know from other domains. For example, vector algebra, complex numbers, quaternions, Blücher coordinates, and also from physics, Pauli and Dirac matrices. And I would like to convince you that geometric algebra is geometrically very intuitive, simple, and compact. And for instance, it is very easy to calculate with basic geometric entities like spheres and circles. So the main goal of geometric algebra is to provide a mathematical language as close as possible to the geometric intuition. Means, for instance, if you want to intersect two spheres, it can be expressed very easily in geometric algebra. You can compute with geometric objects like spheres. They are basic algebraic entities. For instance, if A and B are two spheres, then with the help of the outer product of the algebra, it is possible to intersect these geometric objects, these spheres, and the result of this outer product represent the intersecting circle. And this is not only true for the intersection of two spheres, but for instance, if you intersect a line and a sphere, the 2 points of the intersections are also a specific geometric object in this algebra. And also some geometric operations like rotations can also be expressed very easily. For instance, if you have a line called L in this example, then this exponential describes already the rotation about this line with a specific angle phi. And for those who knows quaternions, it is very similar to quaternions. And what's also interesting, you cannot only describe rotations based on the origin, means around a line through the origin, but it is also possible if you have a line somewhere in space to rotate with this operation also somewhere in space. Okay, so let's come to applications of geometric algebra, and the first commercial product realized based on geometric algebra is from the company Geomerics in Cambridge, UK, and it is a lighting engine for the Unreal game engine. So this is one example that also this algebra is very general. It is possible to realize very fast and performant applications. What we did, for instance, is robot kinematics. In this example, there is a soccer-playing robot, and we realized the kinematics of the legs of this robot based on geometric algebra. And what, for instance, is a nice feature of geometric algebra is that we do not have to consider different frames as we have to do conventional. So we do not have some object frames, some world frames, and so on, but we can realize our application in one frame. That's very nice and makes the application very simple and very compact. Or another application is the approximation of geometric objects to point clouds of laser scans, because it is very easy to handle objects like spheres, circles, and so on. It is very easy to describe algorithms making this kind of job. Or the registration of multi-channel images is also very easy, because geometric algebra generalizes the Fourier transform, and we can handle multi-channels as we normally handle one channel with the Fourier transform. Another application from computer animation that we did is the kinematics of a virtual human, where we also describe the kinematics of the arm and the legs based on geometric algebra. Or finite element solvers can be expressed also easier than conventionally, because rotational and linear parts of velocities, acceleration, or forces, and so on, can be expressed in one expression. We do not have to distinguish between rotational and linear parts. Another application is molecular dynamics simulation that we did on the GPU. And also in this case, it is very easy to handle rotational and linear parts as one expression, and this helps a lot. We did also simulation of electromagnetic fields, for instance. Here we have to use a so-called space-time algebra in order to handle also relativistic effects. And the nice thing here is that Maxwell equations can be expressed only in one expression, only in one equation based on geometric algebra. So these are some properties, some applications of geometric algebra. What is geometric algebra computing now? In principle, it is the combination of the elegance of geometric algebra with high performance and robustness of the implementation. And this is, in principle, what our technology is doing. We have geometric algebra algorithm. Then we symbolically simplify these expressions because they are on a very high level, and we break them down to very easy expressions only with additions, multiplications, and so on. Then in our technology we have an intermediate representation, and then we have a lot of backends in order to generate code for C, C++, CUDA, also for hardware, for FPGAs, and for OpenCL. And this is a link to Mathematica, because based on Mathematica's OpenCL link, we can bring our technology also to Mathematica. And this is done based on our precompiler for OpenCLLink. In principle, what we are doing, we integrate some geometric algebra code into OpenCL code and then precompile it to real OpenCL code. And this OpenCL code is using the vector operations of OpenCL and also uses optimized memory management of OpenCL. Okay, and here you can see a small example from electromagnetic simulation, where you can see how we integrate geometric algebra. It is done with help of some pragmas. The pragma glucalc, for instance, is used to present some geometric algebra code, and then we also need some interface pragmas, pragma GPC, in order to get a connection to the normal OpenCL program. Okay, and as a summary, I hope I could convince you a bit that geometric algebra is very geometrically intuitive. As I told, it unifies a lot of mathematical systems, means that you do not have to translate between mathematical systems. For instance, between transformation matrices and quaternions, if you use these mathematical systems. It is simple and very compact. And for Mathematica, based on our precompiler, it is now possible also to use geometric algebra for OpenCLLink and benefit from fast and robust implementations. So as a reference, I wrote a book, Foundations of Geometric Algebra Computing, which was published last year. I have it with me. If somebody is interested, can have a look. And we had a journal article this year, and this is dealing especially with this precompiler for OpenCLLink. And this concludes my presentation. Thank you very much for your attention.